It's okay. It's okay. I can do the same as Paul. This is okay. Okay. So, first of all, thank you very much for the kind invitation. Paul has set now a very high standards. I'm not sure whether I will be able to reach the standards from Paul. I'm really switching now from really preparing materials to theory. So to really trying to understand how these materials work and how we can get the properties of these materials, and maybe how can we even predict new materials, always, of course, in conjunction with experimentalists, but we want to do that from first principles. So today, what I was planning to do is first to motivate quantum materials. Of course, you all are working already with quantum materials, but I would like to motivate them from the point of view of why do we spend so much time on these systems and trying to understand how we get the origin of the properties of these materials. And then I will go into microscopic modeling and basically introducing to you density functional theory and beyond. So we will see that density functional theory is a very powerful theory. However, it's not the answer to everything, and we have to then do more approximations and more new theories in order to be able to describe, especially in the case that we are here in this cost action unconventional superconductors. And tomorrow I will go on showing to you some examples, and I will, at the end of this lecture today, I will give you a choice and you tell me what you would like to hear tomorrow as examples, and then I will prepare that for tomorrow. Okay, so let's see how far I come. So first of all, as you all know, I'm going to talk about solid state systems, and this is a chunk of iron, I think, and basically this is what it looks macroscopically, but we want to describe properties, so we have to go to the microscopics of the system, and basically this is a strongly interacting many-body system. So in a cubic centimeter, you know that we have the Avogadro number of electrons, so 10 to the 23, all interacting with the ions, and they are basically, I'm going to mostly concentrate on crystalline materials. So materials, like Paul was showing, where we have at the end a crystal where the atoms are sitting in an ordered way, forming some symmetry. And what I want to show is that, in fact, the interaction of lattice with the electronic degrees of freedom give rise to many interesting competing ordered phases. And this is a very nice paper from Phil Anderson, which is more is different, where he basically points to this nice feature of solid state systems, where basically it's not a matter of adding the particles or the constituents. So once you add them all, they basically, through the interactions, they form collective excitation, so you get more than just the sum of the particles. So let me start by just classifying in a very minimal way what interactions I'm talking about. So basically now I'm going to concentrate on the electronic system, so on these 10 to the 23 electrons. And what I'm doing here is I'm showing the basic terms that I would put if I were to write the interactions in a simple Hamiltonian. So I have divided these in terms of single particle interactions and multi-particle interactions, or terms, and then single orbital and multi-orbital. So let me start with the basic term that comes into any system of electrons that we want to describe, which is the kinetic energy. And if I use now the Fock representation, so basically it's going to be these hopping terms, so it annihilates an electron on one side and it creates the electron on a neighbor side. This is single particle, so this is not problematic, so unproblematic, because I can basically put it as a sum of these terms and then solve my system with by looking at what this interaction is doing. There is another single particle interaction which is getting more and more important in the later years. You know about topology, you know about topological insulators and many biosemimetals where graphene, where this interaction is getting more and more in the front. This is a single particle interaction and it's basically the spin-orbit coupling. And I'm going to also talk about it in a while. And then, of course, we have the multi-particle interactions. These are the difficult ones because these involve more than one particle. And whenever we have to deal with these 10 to the 23 electrons, this is what is going to give us a headache. The most important one is the Coulomb repulsion, so that it is, and here I just am showing the on-site Coulomb repulsion, but basically the Coulomb repulsion, the electrons are charged, and naturally they have a Coulomb interaction because of this charge. And the Hund's coupling, if I'm thinking about a system with multi-orbitals, which is definitely this, I can describe it into this way, which basically it's giving me whether electron spins are aligned parallel or anti-parallel, I'm going to gain or lose energy. So now, by just looking at this diagram, I could classify many of my of the unconventional superconductors into different classes, where here I'm putting the interaction is 0, and then here it's growing in this circle. So if I think about the cuprates, basically the main interactions that I have to pay attention to, of course, it's kinetic energy and very strong Coulomb repulsion. And the cuprates, in fact, we can mostly describe them in terms of one orbital, this copper dx square minus y square. So basically, I would have to deal with these two interactions. If I now go to the iron-based superconductors, here, in fact, iron is I deal not only with 1d orbital, but with 5d orbitals. So here, Hund's coupling is also playing a role. It's less correlated than the cuprates, but still I will have to deal with these three interactions to describe these materials. If I go to ruthenides, ruthenium is a 4d system, so the larger I am in the shell that the electron is occupying, it means the electrons are faster, and this spin-orbit coupling is in fact starting to play a role. So spin-orbit coupling is important, either the electrons that are in the core, but for the electrons that are the ones that we are interested in, for transport properties, for all the properties that we described in solid states, these are the electrons in the outer shells, and they start to be relativistic the higher we go in the shell. So therefore, for ruthenides, this is also an important interaction, or iridates. So now, okay, so we classified these systems. Let me now see what is the phenomenology that we know about these materials, and then I will go into the description. So let me start with cuprates. Of course, this is the most prominent example of high TC superconductors. And you know that the cuprates, they have, so Paul was talking about the phase diagrams that he needs for his crystal growth. Once we go into understanding the properties of these systems, we also build up phase diagrams. And the phase diagrams, in this case, this is temperature and this is doping. Since what I'm doing here, my parent compound, which is basically these copper oxide planes, separated here in this case by lanthanum lanthanum or dope with strontium. The parent compound, this lanthanum strontium cuprate, this is an antiferromagnet. So I'm here in this antiferromagnetic phase, but by doping the system, what is happening is that then you are charging, so you are introducing holes into these copper oxide planes, and basically you go into this superconducting phase with very high superconducting temperatures. And in fact, you know that these materials have been and are being studied since more than 30, so since 86, and still we don't know the origin. I mean, there is no theory that explains superconductivity, predicting TC, predicting all the properties. And this is a hard problem because of that, because of the Coulomb repulsion. So here, the copper D electrons are not well screened, so therefore we have to try to find a description where we include also this Coulomb repulsion. And one of the models that have mostly been working on is the Hubbard model, this is a very simple model. As you see, it has the kinetic energy, and it has this on-site Coulomb repulsion. This model can be solved exactly in 1 dimension, but as soon as you go to higher dimensions, here at least 2, there is no exactly solvable solution, and therefore, still nowadays, there is a lot of work being put into trying to get the phases of this Hubbard Hamiltonian. Moreover, when you work with such models, you can say, this is a minimal model, but where do I put the information of my system? So the only information that you have of the specifics of your system, whether you are talking about, here in this case, about this lanthanum copper oxide, or you are talking about IPCO or any other high TC cuprate, where do you put this information? The only place where you have to put this information is in this hopping parameter and in this U parameter. And now the next question that you put is, how do you obtain that? And here is where I'm going to show you that we are going to try to derive this kind of models, oops, the wrong one, yeah, this kind of models from first principles. So really starting from the laws of physics, the information of all the chemistry of these materials, the symmetry, we're going to try to derive these models from first principles. Okay, so this is one example. The next example that I just want to sketch shortly, because I think not many people know about these materials, but they are also very interesting. These are the organic superconductors, and often we call them the little sister of the high TC cuprates, because the phase diagram looks extremely similar. So here I'm showing again temperature, and this is doping, chemical doping. So that basically these materials show, I will show you in a moment what these materials are, but let me show you the phase diagram. The parent compounds are also, most of them, antiferromagnets. You press the systems, and then the systems become superconductors with high TCs. High TCs in the range of energies where you are in this material. So here high TCs is 10 Kelvin. But 10 Kelvin compared to the bandwidth of these systems is extremely high. And what is interesting about these materials is that you can follow this phase transition. This is what we call, these are strongly correlated systems where U plays an important role. We can follow what we call the Mott transition, which goes from first order to second order. I'm not going to talk about that today, but I just wanted to point out that these materials are also very interesting unconventional superconductors. And if you see the structure of these systems, it looks horrible, but it's not. Basically, the structure of these systems is based on these molecules, these BDTTTF molecules. They form pairs, and if I just cut now perpendicular to the plane, these pairs are arranged in a triangular lattice. So basically I have a triangular lattice of dimers of molecules, and now what happens, these molecules are separated by anions, and what the chemistry of this system is that these anions basically suck an electron, one per dimer, so that at the end of the day what I have is a triangular lattice with one hole per side, or one particle per side. So it is the same as in the high TC cuprates. In the high TC cuprates I have a square lattice, here I have a triangular lattice. And now basically by pressing the system, what we are doing is we are changing the ratio between correlation and bandwidth, and that's why you can go from this magnetic state to this superconducting state. So this is also a very interesting system, and the question is, how is this superconductivity raising out of a state which was magnetic? So let me show you, and this would be the minimal model. Let me show you now, of course, a third class of materials are the iron-based superconductors. And I guess Paul will talk tomorrow about iron-based superconductors? Yeah, okay. So iron-based superconductors, again, let's look at the phase diagram of these systems. Temperature as a function here, I'm showing as a function of doping. Again, we go from a magnetic phase. The difference between these materials and the other two classes that I showed is that this magnetic phase is metallic, is not insulating. And then by basically doping, you go into a superconducting state, also with rather high TCs. And how are the structures of these materials? So these are similar structures to the cuprate. So these are layered materials, iron, arsenic. Here I'm showing this so-called 1111, iron arsenic, separated in this case by lanthanum oxygen planes. And basically by doping the system, I'm also changing which is the charge in these planes, and I can then get mobile charges that go into the superconductivity. And Paul, in fact, he is one of the pioneers in these 122 and 1144 materials. He will talk, he has wonderful crystals and there is wonderful physics to talk about these systems. And my part will be try to see how we understand these properties from a theoretical point of view, taking into account that now I will have to be dealing with not only the kinetic energy, but also the fact that Coulomb repulsion is important, and also the Hund's coupling, because these are multi-orbital systems. So if we, by finishing just, no, this is here, by finishing basically this variety of unconventional superconductors, what do we know about these materials? Here I'm showing this picture from the US Department of Energy from a few years ago, where you see this is temperature as a function of the year, so the critical temperature, so when the system becomes superconductors. And you see here this line. These are the line of what we call the conventional superconductors. So these are the superconductors where superconductivity is phonon mediated. And these materials, we understand them very well. I mean, there was the Nobel Prize for the BCS superconductivity. So these are well understood systems. Magnesium diboride, where Paul has been working a lot with it, came as a surprise because the TC of this system is almost 40 Kelvin, and this was not expected to have a material where superconductivity is phonon mediated with these very high temperatures. But these are those that we understand. Now here you see these high TC cuprates with TCs which are really very up to 150 kelvins, and these are the materials which are strongly correlated. It's not a phonon-mediated superconductivity. There is a lot of discussion about the origin of the superconductivity, but correlation plays here an important role. Here down, what we have is the so-called heavy fermions. These are also very interesting materials. Heavy fermions, because here the electrons, the effective mass of the electrons is high, so it's about 1,000 the mass of the electron. And these materials show, in fact, also very complex phase diagrams and also superconductivity, very low, the TCs. But again, these materials are strongly correlated materials, and the superconductivity that comes out here in these systems, in order to explain it, you need to introduce correlations. And here we have, of course, the C60, no, where am I, C60? Well, wherever. They were somewhere here. I cannot find them, but yeah, here. Here are the fullerenes, which are also, again, systems with very high TCs. And of course, here is where the iron-based superconductors start to shoot up. So, okay, so this is now my introduction to this system, but let me just show you the last interaction that I didn't discuss up to now, which is the spin-orbit coupling. So if I now add spin-orbit coupling to basically the phases that I was showing to you, I will have even more interesting new phases. And this phase diagram that I'm showing to you, basically here I'm showing Coulomb repulsion, so how strong is Coulomb repulsion as a function of spin-orbit coupling. Here, Mott insulators is where we were now for the high TC cuprates, for the organic materials, and also for our iron-based superconductors. But let's switch on now spin-orbit coupling, and you see that you go, when correlation is not very important, we have all these topological insulators. We turn on correlation, and you start having also topological Mott insulators, Val-semi metals, etc., etc. Here, there is a very interesting class of materials, which are spin liquids. So spin liquids are materials that don't order at very low temperatures. and they show fractionalized excitations. And a very much discussed spin liquid material are the Kitaev materials. I guess that here Kitaev is probably not interesting, but if you were interested, tomorrow I can talk to you a little bit about Kitaev. So now let me go to the part where I start by how do we describe these systems, starting from first principles. And in fact, our dream would be not only to describe the existing materials, but also to be able to see whether we can predict new materials with very exotic properties. So Paul, okay, I think this is more for chemists than for solid state physicists, but Paul was more talking about that. I will be using more computational simulations. Okay, so let's start by, good, we want to describe this system of interacting electrons, and we have 10 to the 23 electrons. So how do we put the interactions? And you know, this is really a quantum mechanical problem because of electrons. And now what I'm putting together is the interactions I was showing to you. And what I have to do, because I'm in quantum mechanics, I have to solve a Schrodinger equation. So basically I have the kinetic energy of my electrons. This is the Coulomb attraction between the electrons and the positive charges of my ions, and this is the Coulomb repulsion between the electrons. And for the moment, I'm not considering now relativistic effects, and I am considering the Born-Oppenheim approximation, which means that I have already separated the lattice degrees of freedom from the electronic degrees of freedom. So let's start with this equation. We want to solve this Schrodinger equation. However, because of this term, this is 10 to the 23 couple equations, and even if we were to use all the computers of the world, there is no way that we can solve these equations. Moreover, it would be extremely inefficient. The question is, let's assume that we were able to solve this equation. What information do we get out of solving this 10 to the 23? So we have to think about a bit more effective ways of solving that gives us the information we want. So we can think about various ways of having this description. One is indeed to stay in this ab initio, in this first principles basically stage, to try to, just by using what I was showing to you, the fundamental interactions between your particles, try to solve this Schrodinger equation that I have just shown to you. And for that I'm going to introduce to you density functional theory. The second option is, well, I know, for instance, if I have a system, I want to understand, for instance, the magnetic properties or the superconducting properties. Let me concentrate on basically what ingredients I need to describe these properties. So therefore, I go directly to the building of an effective model, like what I was showing to you with this Hubbard model. This is another option that then I will make use of various many-body methods to solve this model. So these are two options, and at the end of the day, because we have interacting systems, so Coulomb repulsion and Microscopic is important, we're going to combine these two ways of dealing with that. So what's the density functional theory? I'm sure that you all know about that, but Herman told me I should do it from the onset, so I'm trying to do it from the onset. So the density functional theory is, in fact, it was really pushed with the Hohenberg-Kohn theorem, which is a very simple theorem, very powerful, but not very useful, just if we stop at the theorem. So the theorem basically, and this can be shown easily, is that the ground state energy of a system of interacting particles is a function of the ground state density. So in fact, you can show that you can express all the properties of your ground state, of your system of interacting particles, in terms of a functional. And this functional is only depending on the density. So you don't need to know the 10 to the 23 degrees of freedom of the position of every particle. It's enough to know the density. So in three dimensions, three variables, x, y, and z, is enough to determine your system. So that's a theorem. This functional exists, but we have no idea how does this functional look like. Therefore, we cannot use it for practical uses. And this was the second important work from Walter Kohn, which is the Kohn-Sham ansatz. And the Kohn-Sham ansatz, that's really the bridge between this theorem and practical use of this theorem. And basically their idea was the following. So we can now, because we know that this theorem is a uniqueness theorem, so that there exists this functional and it's uniquely defined my system through this functional. So what this ansatz says is, okay, let's replace my original system of interacting particles by a system of basically non-interacting particles, that these are going to be fake non-interacting, fake particles, but they are non-interacting. However, they have exactly the same density as my original system of interacting particles. This is the key point, to have the same density. So if we do that, and if we are able then to find out the functional for this system of fake non-interacting particles, then I can use this functional for my system of interacting particles. Okay, so this is basically to map your system of interacting particles into a system of non-interacting new particles where the density is the same. So if you do that, of course, then you can write your density in terms of a sum of one particle wave functions of these fake particles, and you can write your functional in principle as a sum of functionals which contain the kinetic energy, your external potential. So if you have interaction with your lattice or with whatever you have external to your system, you can separate the Hartree term. The Hartree term is basically the term that includes the electrostatic interactions, and you put all the information of exchange and correlation in terms of this functional here. So all your unknown is now localized here. And because you are working with these fake particles that are non-interacting, now you can basically use this functional to derive your Schrodinger equations. And you end up with a set of Schrodinger equations which are uncoupled, basically because these are one particle terms, except that these two potentials, the Hartree and this exchange correlation, are of course a function of your density. So this is going to be a self-consistent set of equations. If you have questions, for those of you that never saw DFT, just put the questions, okay? I mean, you have to stop me. Is it clear what, for those that never did DFT, that now I sort of went from this many-body Schrodinger equation through this process of using the Hohenberg-Kohn theorem and the Kohn-Sham ansatz, I could decouple this equation in terms of a set of non-interacting equations, which then I can solve in the computer. Now, however, you know everything except for this exchange correlation functional, because here, after all, if you're doing this mapping somewhere, you have to put this information of exchange and correlation, and this is put into this functional here. So up to here, everything we did is exact. So this is exact because I'm basically going through this process that I was telling you, but I know everything except the form of this exchange correlation functional. And here is where I have to start now doing an approximation. And this is the next step.
So if I had copper or sodium, something boring, then my VXC would be essentially 0.
If you had copper.
Or sodium. Let me just take the most boring thing. Then
well, it would be very small.
Okay, fine.
It would be very small.
All right.
Yeah, exactly. So you will see that the less you have to, so the less correlated is your system, the better it works. Yeah. So now, of course, we have to think about what do we do with that. Okay. That's the big and what all these 50 years. People have been working on, basically on having good exchange correlation functionals.
You include your crystal lattice into your block wave function.
Yes, in fact, exactly, I will show that. So the information of your crystal lattice, so at some point, okay, so let me say one more thing here. Now let's look at these equations, and let's assume that I know how to deal with that. I look at these equations, these are one particle wave functions, and in fact, correctly saying, this is what we call the Kohn-Sham quantum particles. These are these fake particles. These are not my interacting electrons. However, here we do an approximation. We say, okay, I don't care. Let me just take that as my interacting as the wave function of my electrons. This is the approximation that one does. Now here, you do put all the information of your crystal structure, which electrons you're talking about, which is your lattice here in this wave function. I will show that how we do that, okay? And you start from here, and then you solve this self-consistency that I'm going to show how we do that. And then you will see that you have all the, I call it the chemistry and the symmetries of your system here. You put it into it.
One question?
Yes?
Imagine I want to make a calculation for a semiconductor heterostructure, where I know there is some, due to the heterostructure itself, there is some spin orbit, some kind of.
Yes.
Where should I include it? Just to understand that.
Yes. So you, instead of working with the Schrodinger equation,